please. Okay, hello people. Today is Tuesday, August 16th. Remember, this is the 6th week of the semester, of the second part of the semester. So we are just 1 week short of completing the semester. And I think we are in good shape as far as the material is concerned. So we don't have to be in any hurry. Hopefully we are going to complete it on time with no hurry. Okay, today I'm going to present a couple of slides about the last chapter, and it's about how can we take this information from the irregular response and try to calculate some parameters in order to evaluate the response in irregular waves, okay? I'm going to jump and I'm going to present a table taken from PNA in which it's a nice summary of several parameters that could be employed in order to evaluate the response of shipping waves. Now, I have to warn you because this information is pretty old, right? This version of the PNA was published in '88. So it's about almost 30-something years. So probably I'm going to ask you, I'm going to ask you to consider not only this information, but you have to look for in the literature other parameters specifically according to your ship. So you could use this information in order to evaluate the response of your ship. Please, there's something that has to be quite clear in your mind, okay? All what we need to do is to evaluate. Okay, so let's suppose that you find that your ship has a very large acceleration. It's not your fault, but we need to identify this characteristic. So if you, in the next semester, you want to go on with the development of the project, you know that you have to do something about this response. Something in order to try to reduce for the final design of your ship, okay? So you're not responsible, but the responsibility is to identify this parameter, which is probably very large for the type of ship that you are analyzing, according to the experience that we have with this summary that I'm going to show you, okay? So that's the idea for today's session. That's about 30 or 35 minutes. Then I'm going to say a couple of words about how can we analyze this random signal, okay? And then in the second part of the session, we're going to listen to your progress evaluation, okay? We're going to see how well you are progressing in preparing the final project in this class. Okay, so this is chapter 6. Can you confirm me that you're looking at my full?
Yes, doctor.
My full screen? Okay, good. So, so this is chapter 6, and this is the content of this chapter. We're going to say today something about the sea spectral density considering ship velocity, okay? And the problem is that when you have a velocity, the ship has a velocity, the encounter frequency changes, right? But the energy included, the total energy included in a sea state doesn't change because you are moving in one direction or with a certain velocity. So what we have to do is we have to alter a little bit the spectral density so that if we consider that the ship is moving with respect to the wave with a certain velocity in a certain direction, the total energy considered in the sea state doesn't change. That's the 6.1 point. And then in 6.2, okay, we can take the spectral density and we can decompose it. That means that every piece of this Sea spectrum could be converted into the amplitude of one equivalent harmonic. So if we want to do some time simulations, we can take this spectral density and break it into many, many harmonics and calculate the amplitude of each one of them. Okay, so if we combine all of these harmonics, we are going to have something which resembles the actual variation of the level of the sea surface. Okay, and then I'm going to jump into 6.5 and show you specifically one table, so you have a rough idea what we are looking for in this respect of evaluating the response of shift in a sea wave. Okay, that's my agenda for this afternoon. Okay, so we know that as we can read, the area on the spectral density means energy of the sea. Remember, we did something about that in here. Okay, we said energy per unit area. Okay, and we also divided by the specific weight of the water, since it's a very common concept. And the result is a spectrum. And then we divided by the width of each one of these strips, and the result is spectral density. Now, so the area under the spectral density is energy somehow. Now, this energy, okay, you have a sea state, 3, 4, 5, whatever. You have a certain amount of energy. And this amount of energy shouldn't change because the ship is moving in one direction or another, or with a certain velocity. It shouldn't change, right? So we have to make a correction because of this. That's the idea behind this subchapter, okay? So this is the expression that we remember. So this is encounter frequency is equal to the frequency of the waves. U is the velocity of the ship. K is the wave number, and beta is the angle from the direction of the moving waves towards the direction of the ship, which is also moving with velocity u, right? So we have that. Now, if we get the differential of this, okay, here in K, remember, we also have frequency implicitly, right? So here we have also omega. So we differentiate that, we get omega, d omega from both sides, and this is what we have. Okay, so this is the omega. Okay, this is the width of each rectangle. Okay, very small rectangle. Consider only the wave. And this is the width of a different rectangle, right? Considering the fact that the ship is moving with velocity u and relative angle beta with respect to the waves. Okay, so we have to say that the original area, okay, this is the original spectral density multiplied by the original width, has to be equal to the new width of this rectangle multiplied by the new value of the spectral density. This is a spectral density affected so that its area below this curve doesn't change, corresponds to the original area. Okay, now this WE, we can put it from here. We could replace here. And then you see that we have d omega on both sides. And from here, we can express this in this way. So we replace, we replace this into, we cancel this with that, and this is what we're looking for. So we put this term in the denominator. And this is what we have. Okay, so if we consider in graphical way, the blue is the original sea state. Okay, and now in brown, we have the new spectral density, so that the area below this, okay, is the same as the area from the original function. So since we consider that the area below the spectral density means energy, that energy doesn't change because we have taken care of that, considering that both areas are the same. And this is what we're doing here. Okay, so areas don't change. Okay, so we calculate the spectral energy using any formulation from that we know, Piezo-Moskowitz, ITTC, whatever, and then we affect according to the direction of the ship, and that's our spectral density in terms of encounter frequency. And we can combine this spectral density of the incoming waves with the RAW, response amplitude operator of the ship. And in the RAW, we have to consider the direction and the velocity of the ship. Then we have both spectral density and RAW, both functions of the encounter frequency. And we can go on and combine as we deduced in the previous chapter. Okay, so this is very important. Okay, so that's what I'm trying to say here. We calculate the spectral density, for example, using Piezo-Moskowitz. Then we affect with this formulation. And finally, we combine with rho squared to get the spectral density of the response as function of the encounter frequency. The three steps. Okay, first we develop or apply formulation to evaluate the spectral density of the incoming waves. Two, apply this process in order to consider that the area below the spectral density doesn't change. And finally, we combine the spectral density of the incoming waves as function of the encounter frequency with the rho, that's the response of the ship, at the encounter frequency. We combine these two and get the spectral density of the response of the ship as function of the encounter frequency. Okay. Okay, now the next topic is the composition of the sea state. In certain way, we did this, and I think it's a good idea for you to have it back in your memory. Okay, this is something that we did in the previous chapter. Okay, we consider a sine function, okay, a harmonic function, and we can calculate the mean squared of this single function. So we take the function, square it, integrate it in a very long period of time, and divide it by this period of time, very long. T is very large. So this is a large number. Okay, and this is the result. The RMS squared is the amplitude squared divided by 2. That's for a single harmonic. Now, what happens if we have a summation, a combination of harmonics? So we have something like this. We have a summation, zeta 0I, as this one here, multiplied by sine omega 0I times t. So this is the summation. And again, we calculate the RMS squared. Okay, so we do something like this, but now instead of having one, we have a summation, a combination of these harmonics. So this is this, because if you integrate a sine omega j times sine k times time dt, this is 0. When this frequency is different than this one. So the only values that we obtain different than 0 are the terms in which this omega 0j is equal to that. And that will give us the square amplitude divided by 2. That's what we have here. So that's simple trigonometrics. Now, this is something that we deduced. Okay, we said that RMS squared is equal to the area, and that's equal to, remember, this is equal to the autocorrelation evaluated at tau equal to 0. The autocorrelation, remember, is the inverse Fourier transform of the spectral density. So this is multiplied by e to the I omega tau, but for tau is equal to 0, we have 1. Now, what we can do here is, instead of integrating, okay, instead of integrating continuously from one end to the other, what we can do is we can say that this integral, we can split it in pieces. Okay, and in each piece, we integrate, for example, from here to here, here to here, etc. And this is what we're saying here. Okay? Instead of integrating from 0 to 1 million, we go from 0 to 100, from 100 to 200, and so on. And now we can see that these two summations. So we can say that this area corresponds to the amplitude of this frequency, because we have a very small interval, squared divided by 2. So we can deduce the amplitude, and that's going to be equal to twice this area, and then we have the square root of that. If delta omega is very small, we can assume that instead of having this integral, okay, that's going to be equal to this value multiplied by the width of this rectangle, when this width is very small. And that's what we're saying here, that this integral is equal to the height of this rectangle times the width of the base. That's 2 multiplied by 2, and we have the square root. And in this way, we could take any spectral density that we want. We can split it, we can divide it into small, very small intervals, and with the area of each interval, we can get the corresponding amplitude of the harmonic. For example, we could do this to make a simulation and set the elevation of the waves in a certain sea state. In this case, what we can do is we can take this interval in frequency. For example, in this case, the specific case, we can take, for example, from 0.25, and we can go up to, for example, 2.5. You see that here, the spectral density is very small. Okay, and we can split it in intervals, and we can start calculating the area for each one of these intervals. And with this area, okay, this is this area here, multiplied by 2 and taking the square root, and that's the corresponding spectral, the corresponding amplitude of the harmonic. Okay, how many harmonics do you think it's a good number to do a simulation? Anybody? You can say it has to be a large number, of course, yeah. But how large is large? for you? Any guess? How many harmonics do you think we can take to divide this spectral density in order to make a simulation? Any idea? How many would you take, people?
12 harmonics.
How many?
12.
Some years ago, we received the visit of an expert, worldly expert, University of Trieste, and he mentioned that when he does simulation, he takes 1,000 components. So you have to divide that by very small intervals. So in each one of these, yes, this approximation S times delta omega, it's a good approximation because the delta omega is so small. 1,000. Some years ago, we did some simulation with Marcos Otelo. He's doing doctoral studies at University of Ghent, and we took 100. And we thought it was a large number, but no, still we could increase it. Okay, the computer is very fast. There's not much of a problem. Okay. For example, here in your class note, we have an example. Okay, for example, we have a sea state developed using Pearson-Moskowitz formulation. Let's consider that the wind velocity is 25 knots. So it's about 3 or 4 sea state, sea state 3 or 4. Okay, so with this number, we can develop this curve here. This is a simple exercise, so we could evaluate for these values of frequency. Okay, this is a very small number, about here. And you see that just below 0.5, okay, you got a good number. 0.43, about here, you have 0.05. Below that, you see that there is very, very, very small values. And what we can do now, we can integrate using these values. For example, we could use Simpson rule to integrate. This is what I'm doing. Okay, so I integrate from 0 to 0.25 cycles per second. I'm sorry, radians per second. And then I integrate from 25 to 0.5. This is what I obtain. For a very small frequency here, basically there is no area, and that's why up to 3 decimals, I got 0. Here, in this area here, we have a little bit of area here, and we obtain an amplitude of 0.166. So this is sigma 0.1, this is sigma 0.2, and we could go on. And these are the results. Okay, for 0.125, this is the central frequency in this range. Basically, the amplitude is 0. That's what I have here. For 0.375, I got 166. That's what I have here. And then I can go on. You see that the amplitude increase because we have more area in this part, and then start decreasing. Okay, and again, what I do is I generate a phase shift. This is an angle. Well, I generate it in a random way. Okay, this is easy to do using Excel. And after that, I just can combine. Okay, I have, for each one of them, I have amplitude, which is this number here, frequency, and I have this phase shift, which is random number. And this is the result, for example. And you see that this maximum changes in time, because it's a random process. So in this case, I took 7 elements of the of this series, and you see the random shape of the function resulting. Could use much more larger number, but since this was a simple example, I just took 7. Any questions, people, about this? Any questions about this? Now, just in case maybe you need to do some. Okay, before we go on, I'm going to jump to the last part of this chapter. Okay, I want to show you a summary of parameters and recommended values in the 80s. That's last century. Okay, according to the type of ship, according to the type of special operation that they develop. Material will be reviewed on Thursday. Okay, this is the summary that I want you to have in mind. Okay, this is taken from PNA Vol 3, Volume 3. Okay, this PNA version was edited in 1988. Let me write it here because it's so important. This is, okay? What we have here? What we have here, it's a summary of many, a lot of sources of information. You see here, these are the sources, okay? And we have a list of parameters that you can employ in order to evaluate this type of ships. So here, you see that mostly we have the RMS value of something. The RMS value of the roll angle, this is degrees. RMS value of pitch angle in degrees, etc. There, we have the motion sickness incidence, okay? This parameter you see is 20% in 2 hours, 20% in 2 hours, 10% in 4 hours. What does this mean? This means that if you have a group of persons on board, okay, you could have no more than 20% of the people vomiting in the ship after 2 hours of exposure. That's the meaning of this parameter, okay? So if you have a large percentage of the passengers who are vomiting, that means that the ship is moving too much. Okay, so that means that we have to do something about it, okay? The acceleration of a slam in units of G. This is slam frequency. This is also very important. You see that this is 3/100 or 20 in 1 hour. Okay, that means that you have 20 of these slams in 1 hour. If you have more than 20, that means that probably your ship is banging against the surface of the sea too much. And that probably will start affecting the proficiency of the crew or even the equipment. So we have to do something, okay? There are a couple of things which are very interesting here. For example, deck wetness frequency, okay? That means that, okay, so you have the bow of the ship moving like this, and you have the surface of the sea moving like that, right? If both move up or down, the distance between them doesn't change. But if one moves down, if the other moves up, there's going to be some relative motion. If this relative motion is larger than the freeboard, that means that the surface of the sea is on the deck. and we can expect water coming into the deck. That's what we call deck wetness. Deck wetness. That means that the water reaches the deck. Okay. Now the problem is that something like that happens. For example, 1 every 2 days. Nothing happens, right? Because you have water, they flow, and the deck gets dry again, and nothing happens. The problem is that you get one deck wetness, and before this water flows downwards from the deck, you have another deck wetness. Then it's possible that you have accumulation of water on the deck. That the kg increases, and also since it's water, you have a free surface effect. Okay, so you have to be careful because you cannot allow these phenomena to occur too often. And that's why, for example, they say they recommend this value of about 30 in 1 hour. If you got more than 30 in 1 hour, this author is saying maybe there is a problem there. Okay. Similarly, for the propeller emergency frequency, what does this mean? Again, you have the ship. Okay, let's suppose that this is the aft. Here you have the propeller, right? And you have the surface. If you do something like that, that means that the propeller is out of the water. If the propeller comes out of the water, the resistance of the fluid in which the propeller is moving suddenly changes from water to air. That means that the resistance decreases because the air is about 1,000 times less dense than the water. So since you have less resistance, the propeller basically races. But then comes again into the water. So it accelerates and then deaccelerates. So the system, propulsion system, suffers a lot. Okay, so you have to restrict the number of times that the propeller comes out of the water in a certain time. So here you have values, for example, it says 25 in 100. So let's suppose that you have 100 cycles. Of those cycles, you cannot go beyond 25 times where the propeller is able to come out of the water, because that will definitely damage the propulsion system. Okay, so you can use any of these parameters in order to judge, okay, the response of the ship in irregular waves. Now, what ships are we talking about? Well, these are the ships that we're considering. Okay, these up to here are Navy ships, and in the right are commercial monohulls. Okay, if there is one design which refers to a naval monohull, right? Okay, for example, this source recommends these values for these parameters. Okay, now one of the problems with this is that you see that this author recommends 9.6, but this other author, even though both are naval monohulls, recommends a very different value. Okay, so we have a problem there. What we can do is we could try to see if there is a more up-to-date information about this, the maximum allowable value for this parameter. Okay. As far as the commercial monohulls, for example, here we have a trawler, that's a fishing vessel, and we have some values that we could use. Okay, for example, they evaluate the RMS vertical acceleration. Okay, so we have to calculate the, usually this is the largest vertical acceleration are developed when you receive waves from the forward end. Okay, in that case, the the pitch usually increases a very large amount. And remember that you have to combine heave and pitch in order to calculate the vertical motion of any point along the length of the ship. Okay? You have to calculate the spectral density. Okay? The area on the spectral density corresponds to the RMS squared. And finally, you get the square root of that and get the RMS. We have to be careful with the units. Remember, this is engineering. Okay, people, is there any questions about this? Any questions about what I've just explained it?
Doctor, I have a question.
Yeah, go on.
So you say that we just have to analyze to compare, right? So it doesn't matter if the value that we obtain, for example, for the MSI is higher than the value that the table says. So it doesn't matter. So we just have to comment about that.
Yeah.
All
see,
right.
all what we need, see, because the problem is this. Right now, you do the design and you have to evaluate the design according to any parameter. Now, if this were a real world, right, probably what's going to happen is this. Let's suppose I am the ship owner and you are the engineer, naval engineer, who is going to design the ship. Okay? So I'm going to ask you, please design me a ship, okay, to provide passenger service for the Galapagos Islands. But I am asking you, but please try to make it doesn't move too much, because otherwise the passenger will get seasick. But the problem is that there is no numbers in that, right?
Yeah.
That's the problem. So let's do this in a very professional way. What can we say? Okay, the design has to have no more than 30% of people seasick in sea state 4 after 2 hours of exposure. So when you deliver the ship, okay, you give me the design and I build it. I build the ship. I take the ship to the sea and I expect a sea state 4 or 5, whatever. And I have 30, 40 people on board. Start seeing, after 2 hours, how many are vomiting? If that's more than 30%, that means that you have not designed correctly the ship. So right now, you need to calculate the MSI. And if you find that this percentage is higher than 30, before you take the plans with the ship owner, you have to do something. Maybe you have to consider, for example, installing these active foils. Definitely you have to install bilge keels or something, or make it larger or something like that, so that you try to reduce in numbers, in your calculations, you try to reduce the MSI, the motion sickness index, in the passengers before you build the ship. Before. Okay, so in this way, that's a way in more advanced situations, the ship owners and the designers get together and start putting numbers in so the response of the ship that they employ in order to evaluate if the design is correct or not. Mr. Galarza?
Yes, doctor, yes. Thank you very much.
No problem. Right now, since this is just the preliminary design, okay, it's a good idea if you end this project concluding that you need to do something in order to do this or that, to reduce this or that response parameter. Okay, so I'm going to ask you to consider 3 parameters. Okay, now, since this is very old, this is 1988, I'm going to ask you to allow you to use 2 parameters from this table, and you have to find out another parameter from another source, okay, closer, I mean, more up to date than 1988, okay, in order to evaluate your design with that parameter also. So you need to evaluate 3 parameters. 2 of those could be from this table, and another you have to find according to the type of your ship, okay? And you have to calculate it, and in the end, you can evaluate. For example, this morning I was looking with Miss Sayu, and she showed me that in MaxSurf, it is calculated the percentage of increment of the resistance. So it could be a good idea if you find a paper or any source of information in which they compare values of acceptable increment in the ship resistance from the irregular waves. Okay, that could be a good point for the fishing vessels, right? And please don't show me references below or before 1988. They have to be references from newer than 1990 or something like that, okay, in order to be valid. Okay, questions? Any more questions about this, people? Okay, don't worry. This deck wetness frequency and things like that, I'm going to show how can we calculate using what we know as the moments of the spectral density. Okay, so you calculate the spectral density, and then you calculate another parameter from that distribution. Okay, and those parameters allow you to calculate these frequencies. Okay. Okay, let's take a break here. 4:53, 5-minute break, and when we return, I'm going to say 2 words about how can we analyze the random signals, and then I'm going to listen to your progress reports. Okay, Ms. Sayo, would you please stop the recording?